Welcome back. This is part two of our presentation on inverter types and considerations. And in this part, I'm going to talk in a little bit more detail about the system grounding on the DC side as it relates to the different types of inverters that we talked about in part one. So starting off with the transformerless inverter type system, this is also known as a TL inverter or a non-isolated inverter. We have our DC from the PV array coming in on the left side and our AC to the grid or primary power source on the right side. And what's happening in the inverter is we have a functional ground connection from the DC conductors to ground via a high impedance connection in the inverter electronics. So it's built with its own circuitry internal that will provide ground fault detection and protection via that internal circuitry. So the connection to ground only happens after the system turns on. And so in order for that system to turn on, it does its own insulation resistance test every day. And once it passes that test, the inverter will turn on and the DC conductors will have a functional ground connection. So taking a look at what a line diagram for this type of system looks like, we have our equipment grounding conductors, which connect all the metal parts of our system together. And you can see it goes from the array, that green line, all the way around through the disconnect, the DC disconnect, into the inverter, and then the connection proceeds to continue through the AC disconnect and into the primary AC power source. Next, we have our functional ground reference inside the inverter through the inverter's internal circuitry. And then you can see here, this is where the system ground happens. This is the bonding jumper between the ground and the grounded conductor. So you can see there's the AC grounded conductor, and then we have the AC ungrounded conductors. We also have our DC conductors, of course. Now we're going to take a look at an isolated inverter type system where we have a transformer based inverter. And so same thing, DC on the left side from the PV array, AC on the right side to the grid or the primary power source. And this is going to look a little different from our last inverter configuration. So notice there is a functional ground connection from one DC polarity to ground via a single point on the PV-DC circuit. So what that means is we have a connection to ground through a ground fault protection device inside the inverter. In most cases, that's going to be a fuse, like a 1 amp fuse, a 2 amp fuse, maybe a 5 amp fuse. And so that connection to ground goes from whichever, in this case, that black conductor would be the grounded conductor. It's connected to ground through that fuse, through that ground fault protection device, which contains a fuse. So the connection to ground, as I said, typically would be through a fuse or some type of a breaker, and we don't want to duplicate that connection externally. We only want to have one point where the DC conductor is connected to ground. Okay, so taking a look at a line diagram for this type of a system, we have a lot of similar parts. Here are our equipment grounding conductors, which are bonding together all the metal parts throughout the system, from each module frame, through the DC disconnect, through the isolated inverter, through the AC disconnect, and then back to whatever type of a panel is providing service from the AC power source, that primary AC power source. From there, we have our functional ground reference through the ground fault protection device inside the inverter. So this is slightly different from the electronics that we saw on the TL type inverters. And then we have our AC system ground. That's also shown as a bonding jumper here. And we have our AC grounded conductor. So that bonding jumper is the connection between that AC grounded conductor and ground. And then we have our AC ungrounded conductors, these two black and red conductors here. And we have, of course, our DC ungrounded conductor on the right, the red in this case. And in this case, we're showing the DC functionally grounded conductor as that black conductor. And you can see if you follow that black DC functionally grounded conductor through that DC disconnect into the isolated inverter, there is a fuse in there, kind of goes into the inverter through the fuse and is connected to ground at that particular spot. So why does this even matter? We're talking about all this stuff. Well, it really kind of doesn't matter because the NEC Article 690 requirements for fusing, system and equipment disconnects, all of grounding and bonding, wiring methods and materials, arc fault protection, ground fault protection, rapid shutdown, all of it are the same. All the requirements are the same for transformer-based and transformerless type systems now. So this is a newer development in the National Electrical Code, but they have made it a little bit simpler in the sense that all the requirements are the same for both types of inverters. It's important to understand the differences between those two types of inverters, but at the same time, understand that the requirements are now all the same for both types. I'd like to touch on one other type of functionally grounded inverter topology, and that's bipolar PV arrays. So what does that mean? Well, we have half of the array is positively grounded and half of the array is negatively grounded. And each of those halves is known as a monopole subarray. And there is a common reference point within the inverter that is a series connection between both monopoles. And so you have to have a very specific inverter that is a bipolar inverter to make this happen. You can't just wire an array in this way with any old inverter. It has to be a very specific bipolar type inverter. And these are few and far between these days, so you might come across these on a legacy system. You might come across it performing any maintenance on an older system, and they may come back into fashion at some point, but they're not terribly common as current methods of installation. That said, I think it's important that you understand that they do exist, and when you come across one, this is kind of what you're looking at. And so this is just a quick little overview of what to look for and how they look in terms of their wiring. So half a positively grounded monopole subarray and half a negatively grounded monopole subarray. This diagram shows it pretty clearly. You can see the grounded conductor on the upper half is negative and the grounded conductor on the lower half is positive. And so that's kind of the split, and then the series connection happens in the inverter at that point in the center, and that pretty much is going to cause the voltage to double. So for example, if you have two 550 volt strings, one negatively grounded and one positively grounded, they're connected in series, and that's going to bring the voltage up to 1100 volts. So one thing to note with this type of a system, each monopole circuit has to be physically separated from the other, and they are required to be located in separate raceways, and that's an NEC requirement. So that's just one thing to note for this type of a system. That's important in terms of requirements. And so bipolar PV systems in the field, you are unlikely to be installing these as new systems, these days, but you may encounter them for maintenance and service as a legacy system. And there may be new bipolar equipment that's manufactured and used in the future. We don't really know, but if you do end up working on these types of systems that are older, you want to make sure you get an accurate copy of the manuals from the manufacturer for the equipment that you're working on, and really understand the specific wiring requirements and everything else that goes along with it before you attempt to do any maintenance or service on this type of equipment or this type of an array. Well, that's the end of part 2. Take a break and come back and join us for part 3 whenever you're ready. We'll be talking about module level power electronics.